So welcome everyone to this first kind of opening session at Edge 2022. I really love presenting at Edge year over year, and normally I'm talking about things that are coming, right? What the future looks like, the things that are on our roadmap. I share Leighton's excitement about the API capability that we delivered in August of this year. So we have an open platform now with APIs where you can push data in and you can extract insights out and you can feed downstream processes. So it's super excited. It's super exciting for me as our platform is really reaching maturity. But I'm not going to talk about the future. If you want to hear a lot more about, our coming capability, I've got a little bit. I will say a little bit about it because I can't resist. If you want to find some more about what are the cool things that we're doing in the lab, what is coming, I recommend that you stick around for Rachel's session, Rachel Kirkham, my awesome colleague who's going to be presenting after. And I think that session is going to be super interesting if you want to know a little bit more about what's coming. I'm going to talk a little bit more about scaling our platform and what that journey has been like. Leighton also talked about how MindBridge has been in business for 7 years, something like that. I've been here for most of that, and I want to describe a little bit about the scaling journey we've been on and how far we've gone. We actually achieved a milestone earlier this year. We've not publicized this particularly, and I'm going to talk about it. You'll find out what it is later in the presentation. And it's really something that's quite exceptional. The level of scale that Leighton talked about, where he hasn't seen an organization or a technology team do this before, or quite as well as the MindBridge team. I share that opinion, and I'm going to talk to you a little bit about how far we've come and how we got there. So again, I've been with MindBridge since the beginning, so since 2016. There's a picture of me in 2016. That's one of the first presentations we did at MindBridge. That's actually in the Mars Discovery District in Toronto. And we talked about how building trust in AI was so important. You see that in our algorithm validation. We just did an entire seminar on building trust in artificial intelligence systems, what to expect, how to do it. Yeah, I mean, we've been doing this for a while, and we were probably the first to start talking about that. And we have many firsts along the path. Let's get off this screen. We're going to talk about what we are actually going to do today in this session. So I'm going to talk about our journey into unknown unknowns. We talk a lot about how data needs to speak for itself, and that's the only right way to find things that are unexpected in your data, things that you need to know as well. So, I'm going to talk about how our technology is able to discover things that are impossible for a human to find, right? And we're going to do some kind of fun experiments to show how difficult it is for a human to spot something that a machine can spot fairly easily. Now, the next thing is, once you can do that, you then need to figure out how to scale it. And it turns out that scaling this capability is really hard. Like, I don't mean just kind of hard, I mean really hard. So MindBridge has been working on this problem, again, for years. We've kind of cracked this, right, at this point. And this has put us in an unprecedented position to be ready for the future of outlier detection across many different financial data sets and across many different industries. So, go to the next slide. If you visited the MindBridge offices, which is actually where I am today, you'll actually notice there's a little bit of a Star Wars theme. So, and Star Trek fans tend not to, tend to feel a bit left out. So this slide is for them. So I started thinking about how long we've been doing this, right? This has been a 5-year mission for MindBridge. Our data exploration into unsupervised machine learning to find anomalies has been, it's been extensive. I was asked the other day, and again, this is by a CTO in a different organization, how many different anomaly detection algorithms we had tried. And my answer was, we've tried all of them. I don't think there's one that we haven't tried. So we've done a lot of research. We figured out what works. And it's been a real kind of voyage of discovery, right? And we think we've found something that's really important. Now, there's a geek warning on this slide as well. Yes, I am a little bit of a geek. I am going to be talking about some of the technical challenges in scaling the algorithms that MindBridge has, but I'm going to try and make it understandable so you don't need a PhD, you don't need to be a computer scientist to actually get this. So it is going to be a little bit technical, but I'm going to make it fun and understandable. So incidentally, a quadrillion is a million. So that's quite a lot. That's the actual number of comparisons you have to do on a 500 million row data set. So everyone can imagine what a 500 million row data set is, or how big that would be. A quadrillion is the number of comparisons you have to do if you have to compare every row in that data set to every other row. I've been presenting about data analytics for many years, and I've quite often had a slide that talks about the data explosion. And it's often very difficult for people to grasp how big the amount of data we're currently processing is, both at MindBridge, but in the world in general. There's a Forbes study that says that we are generating 2.5 quintillion bytes every day. Quintillion is bigger than a quadrillion, by the way. It's a couple more millions you got to add on the end. I think it's 10 to the 18 is the 10 to the power 18 is how many zeros you have to put after 2.5 to get to a quintillion. Now, how big is that? It's really hard to kind of grasp how big that is. So if I take a hard drive out of a server, let's say it's a terabyte hard drive, those are serially attached storage in a server. Those are typically about an inch high. If I was to take an inch high hard drive, and I was to stack them up, one on top of each other, I'd get to about 110 terabytes if I stack them to the roof here in this room. 2.5 quadrillion bytes would require a stack of 1-inch hard drives that's bigger than the Empire State Building. That's why there's a little Empire State Building on this period. It's actually 140 Empire State Buildings stacked on top of each other. That includes the antenna, by the way, on the top of the building as well. So that's quite a lot, all right? If you were to continue to stack hard drives for a week, and this means that the amount of data that we produce in a day is 140 Empire State Buildings tall. The amount of data in a week is the tower of hard drives would reach the International Space Station, which is it's in low Earth orbit, and that's about 400 kilometers high. Now, this 97 zettabytes, again, zettabytes, one of these unfathomable numbers. That's how much data is stored in the world today. MindBridge is a part of creating some of this data as well. As Leighton said, we're storing over 50 billion data points about how our platform has been working. If you were to store that and the stack of hard drives, it would reach all the way to the moon and back, and then back to the moon again. So it's about 3 times. So these are huge amounts, the unfathomable scale of data. And this is kind of a big problem for the world in general, a big problem for people to be able to leverage it, right? And in fact, only less than 0.5% of all the data that's created is actually used in any kind of meaningful way. So why do we care about this data? Why do we care about the explosion? You know, we've got cloud, we've got compute in the cloud and storage in the cloud. Surely that's just taking care of it. Well, yes and no. Storing it is one thing, right? But leveraging it, analyzing it, extracting value from it is, as it turns out, is actually quite hard. And this is actually, again, a part of the journey at MindBridge. It's all about leveraging data to create new value and create better outcomes. So solving this kind of data analysis problem it's a big problem from the world in general, and MindBridge is a part of that. But if you can do it, really exciting things can happen, right? So this is a quote from Naval Ravikant. So you might not recognize the name. Naval, I'll read the quote. "The rise of the data era, coupled with software, creates an opportunity for some companies to outperform others." Naval is a little bit of a visionary, right? He was a seed round investor in some companies you might have heard of. For example, Twitter and Uber. He was in the seed round. That means like before other people realized these were good ideas, he was there. So he's predicting that software combined with data is going to create the opportunity for companies to outperform. It definitely creates a competitive advantage. And you know, I was reading just a couple of years ago, McKinsey paper on And the title of the paper was "The Recovery is Going to be Digital." This is talking about the recession and COVID that we've all experienced in the last few years. The recovery is going to be digital. This means more companies are looking at how can they use data and software to create advantages for themselves. Another quote which kind of backs up, like, using data is a good idea. Let's figure out how we can get value from it. This is the CEO of Bank of America, and he talks about technology is going to lead the change in how companies are organized. And certainly we've seen this. We've seen if you look at the usage stats, for example, at MindBridge, you'll see that year over year, the amount of data flowing through our platform is just doubling and doubling and doubling, right? That's a power expansion. That's doubling and doubling. That's a lot to worry about there. We are thinking a lot about how we cope with the data volume at MindBridge and where we are going. Now, this is a slide which actually comes from probably 5 years ago, when we started to talk about what's our purpose, what's MindBridge's goal here, what are we trying to achieve? And we were looking at this world of data as being an iceberg, that only the top of it is really analyzed in any kind of meaningful way. And that's also true in financial data. It's also true in the kind of ledgers and data sets that are used in audits or in kind of financial data governance. It's fairly easy to just scratch the surface and then find things that are the known problems in a data set. But if you're actually trying to go beneath the surface, so this is where the iceberg analogy really comes in. If you're trying to find things that are unexpected, you typically can't use rules-based approaches. You typically can't use things that are not AI or machine learning based. And certainly, if you're trying to find some unknowns, things that you really are, you genuinely don't know are there, but which matter to you, right? You're not going to solve it with spreadsheets or kind of human level eyeballs looking at the data. You need a machine to help you analyze that. And that's really the premise that MindBridge started with, that we can build an AI system, we can build a technology that can look at vast amounts of data and derive new value, which creates new insights that bring competitive advantage to our customers. This was our original purpose, and it's been there from the very beginning. I just want to talk a little bit about reasonableness, the reasonableness test. My family are largely lawyers, not software engineers like myself. So reasonableness test is, at law, it's a question about what a reasonably, suitably skilled person would do. You can actually call this is one of the state-of-the-art tests as well. What a reasonably skilled person would do in a similar circumstance. Now, the reason I bring this up is because reasonableness is a function of contemporary opinion and methods, right? And when MindBridge started 5-6 years ago, using AI to analyze financial records, to find unknowns in those financial records, that was a new idea, right? We are 7 years from when we started, and you've seen the growth that we've announced, in the usage of our platform. I would argue that what's reasonable today has changed, right? And this means that contemporary technology like MindBridge is now considered a reasonable thing for a suitably skilled person to use in order to understand financial data. And we've built this using a combination of different methods. Again, you've probably seen this before. We use an ensemble AI. I'm a big fan of not relying on a single model system. So using multiple different models to analyze data in lots of different ways in order to really find out what's going on. So why machine learning is so effective at finding unknowns? Like, we're going to do some experiments. I'm going to show you why it's so good at this. But the sort of things that are great about the kind of machine learning that MindBridge uses is it's unbiased. Our algorithm audit says that we have a green light on bias, right? And that's a part to do with how we design the algorithms. It's also tireless. It never tires, and it's able to find detail no matter what. A detail that an ordinary human being, could work with data for years and years and not spot the problems that a machine learning algorithm can. And that's in part because machines are able to think in many dimensions at the same time. And we struggle with 3 dimensions. We certainly struggle with 4. So we're going to do a couple of little experiments later on just to illustrate this point and to show you how good algorithms are at finding things that human beings can't. So just a couple of little definitions to get us started. The machine learning, there are a couple of different branches of machine learning that exist. There's a type of machine learning called supervised machine learning. And another way of describing this is it's an algorithm that learns from labeled data or labels, right? So what it can do is it can do things like learn how to categorize a data set. A very simple form of supervised machine learning is a method called logistic regression. So it's actually quite an old method. It's actually very commonly used as well. If you did linear regression at school, and most of us did, fitting a line to a graph, logistic regression is kind of mathematically similar. It uses something called a polynomial expression to create what's known as a decision boundary. And it's a little bit more involved than linear regression, but basically what it does is it learns from labels what is the best way of categorizing data. And it generates this chart at the bottom is fairly common kind of logistic regression outcome. It's trying to categorize what things are X's versus O's in this data set. And it's kind of drawing a little ring after it's finished saying, this is your best prediction. If it's one side of this line, then it's an O. If it's the other side, then it's an X, right? So it's a very simple method. And it's a part of this supervised machine learning. Deep learning is also often, there are exceptions to this. It's mostly a data set that will learn from labels. And the problem with supervised machine learning is, what are you learning from, right? Are the labels that you're learning from good? There's a quality of data problem. And is it going to work in every different circumstance, right? This is one of the problems with data sets that can bring bias and understanding bias. You really have to think deeply about when you're using supervised machine learning, if it's always going to work, if your model's going to start to become less accurate over time because the world changes, that sort of thing. So supervised machine learning it's great. It's typically quite efficient when it works, right? But it can't cope with circumstances it's never seen before because it learns from labels. You have to tell it what it needs to learn, right? It can't find things that are new, right? So this is a point of unknown unknowns. You can't find an unknown unknown with supervised machine learning. It has to have learned to find that thing, right? So conversely, there's another type of machine learning called unsupervised machine learning. And this doesn't require any labels. In this example, I use an algorithm. And again, you don't have to read the code on the screen. There isn't going to be a test later. But this is an example called k-means clustering. So in this example, what we do is we take a set of data sets. This is the kind of blue data set there on the left. And you can see that all these points they're just they're all blue when they start. They're not categorized in any particular way. What this algorithm can do is you say, hey, I need you to find 3 groups in this. I need you to discover groupings in this data set. Go find me 3, right? That's what it's doing in this example, at least. What it does is it creates 3 points, which it calls centroids, and it figures out the distance from the centroid point to all the other points, and it keeps shifting the centroids until 3 clear groups emerge. And when the groups stop, when points stop exchanging groups, it's reached a stable state and it's discovered 3 groupings. Now, this works really well at finding, discovering groups in data sets. In itself, it's not an outlier detection method, but it can be adapted to become one. But it's a great example. It's one of the simplest examples of unsupervised machine learning. It doesn't need to know anything about the data set to find the groups. It will just discover them itself, right? And that's the kind of algorithms that MindBridge is typically relying on. Now, we're going to go into a bit of detail on a specific algorithm that's in MindBridge. And the reason for this is because I think it's cool. I'm going to explain how it works as well, and how it works in a really kind of clever, maybe slightly non-intuitive way. I'm going to try and make that intuitive for you with some examples. This algorithm itself is a part of the outlier anomaly control point, which we all know and love. The algorithm behind this, which is again exposed in our documentation and audited by University College London Consulting, is called stochastic outlier selection. And it was first proposed in 2012, so it's quite a contemporary algorithm by Jerwin Janssens from Tilburg University. Actually, this was a part of his PhD thesis. So the theory behind this is that financial data sets contain information which is a reflection of a business process in some way. So if you imagine that the data is all a reflection of what the business is actually doing, it's actually, or ledger transactions are a reflection of business processes, so invoices, expenses, payroll. These are, it's basically a microcosm for what the actual business is doing recorded in transactions. If you imagine that that's what's actually happening in a ledger, what you can do is say, well, there's probably groups of transactions that look like one thing or another. There's going to be a group of transactions that look like expenses. They all probably are between a certain dollar value. They have a certain number of lines in them. They might mention an employee. They're probably happening at some periodic interval. Maybe it's going to be monthly expense payments, that sort of thing. So once you understand a little bit about what's going on in a data set, you can say, well, perhaps we can discover these transaction groups using a non-supervised learning algorithm, because we just learned that k-means clustering can find groups in data. So what SOS does is actually, it's a two-step thing. It actually discovers the proximity of points to each other, and it looks for things that don't look right, things that are further away from other things. We're going to talk a little bit more about how it works. And again, there's not going to be a test on how the algorithm works, but I am going to talk about some particular parts of the algorithm to explain how it works. Stochastic outlier selection it's based on something called affinity, and it's all to do with neighborhoods, right? So the way the most kind of clustering algorithms work is they work on something called distance. So the distance from one point to another tells you how close they are. Affinity is a slightly different property, right? It's all to do with neighborhoods. So let me explain. So see this diagram on the right-hand side there. You see these, there are some orange points and there's a blue point. And if you were to look at this with your eyeballs, you'd say that blue point probably is the outlier. Which is true, it is, right? Now, what's interesting about affinity is about a data point's affinity for others, right? So you have an affinity to other data points around you, and it's all related to how densely packed the points are and the neighbor distances. So in this example, the yellow, all the orange points are tightly packed, right? So they have high affinity with each other. They're close to each other, and they also know about each other, right? Conversely, if you look at the blue point, right, it's further away, right? It actually thinks that these other points are its neighbors, but those neighbors don't think they are, right? They don't think they know about the blue point. So maybe a better way of imagining this is, let's say that this is a neighborhood, right? And you want to borrow a cup of sugar from someone in your neighborhood. If you're one of the orange points, you're going to go to one of the closer points to borrow a cup of sugar. You have high affinity for those neighbors because the distance to them is less, right? But you're not likely to walk all the way to the blue point to borrow a cup of sugar because he's just too far away. So the other thing to realize about this algorithm is your opinion of your affinity is not important. It's the opinion of your neighbors that matters. So all the orange points think the blue point is an outlier. The blue point doesn't know it's an outlier. It thinks its neighbors are the orange point. So it's kind of, it's the reverse intuition, right? So only other points impact whether you're an outlier or not. And it's a bit like this cup of sugar problem. You're figuring out who you have high affinity for and who you have low affinity for. Now, why is affinity important? It's actually one of the calculations in this algorithm that's kind of hard to deal with. We're going to talk about that in a bit, but first I'm going to show you how well this algorithm actually works. So this is a set of diagrams from the paper that was published. This is a part of the PhD thesis, right? And each column in this diagram is a different algorithm type. There are, I think, 2 of these algorithms are used in MindBridge today. The column that's the far right, the one that is closest to the banana, is stochastic outlier selection. That's this algorithm we're talking about. Now, the first row is a different, it's the algorithm, how the algorithms work on a particular data set. That data set is in the shape of a banana. It's a synthetic data set, but what they're trying to demonstrate is how well this algorithm works at understanding the boundaries, right, around things. How well it, so this means essentially that if you look at the blue point in the center of that banana there that's at the top right, that's a neighborhood. That's saying that all of these things have high affinity with each other. The further you get away from blue and as it goes to green and red, those are the areas where outliers would live. And if you're in that area, it's likely one of these kind of low affinity areas. But look at how the other algorithms deal with it. There's a banana shape. You can kind of see-ish that there's a banana in the next 2 that are closest to it. But look at the ones that are on the left, right? That's just the blob, right? These are much simpler kind of density-based approaches from stochastic outlier selection. They don't use affinity, so they're not able to create these boundaries around it effectively. So what we can say is that stochastic outlier selection is really good at closely identifying neighborhoods and finding things that are close to, but sufficiently different, right? This, it's a point that thinks it's close, but it's just not quite close enough to be considered normal. So let's try it. This is something that I created in the last few days, the banana test. Spot the outlier. So here is a data set. And there's only 9 points here. And I want to see if you can pick out where the outlier is. One of these points is not like the other. And this is called the banana test, and you'll understand why in a few minutes' time. So I'm going to give you a few seconds to look at this and pick out which one do you think is the outlier. It's quite hard. By the way, I've had people tell me, oh, I don't need outlier detection. I have Excel. What I can do is I can take this column of numbers, I can sort it from high to low, and I just have to look at the highest and the lowest, and those are going to be my outliers. Yeah, true, but I'm going to show you why that is really not sufficient, right? And really not sufficient on a data set like this, particularly where you have more than one dimension. That sorting thing doesn't work, but also when you have a situation like this. So the answer is C. This is the outlier. It's not the highest point in either direction, but if I plot these points, you'll start to see it. It's pretty obvious that that is the outlier. So if you're using stochastic outlier selection, it will find this point. By the way, you probably need a data set that's about the size of the one that's on the right here. That's about 50 points. It'll work well on that. 9 points is not very interesting, but at a human level, we can't. It's hard for us to pick this out of a group of numbers. Easier when it's visualized. But you have to imagine this in multiple dimensions that are hard for us to perceive. So this is an example of why machine learning is good at finding things, and also an example of why just looking at numbers on a page won't find it. Now, the reason this is difficult to find when you sort is because the X and Y coordinates of this point are in the normal range. This point is actually right in the middle of both of the X and Y normal ranges. It's just further away when all the points are considered together. So again, a great example of why this type of algorithm is useful for finding outliers. Now, there's a huge problem with SOS. It's actually, this is true of a lot of outlier detection algorithms. There is a point when they're describing how this algorithm works where they actually, this is a quote from the paper, we compute the affinity that each data point has to every other data point. So on a data set, this means that for every point that I put in, I have to compare that point to every other point in the data set. So this is the calculation of affinity. So that's quite expensive from a computational standpoint, right? That's in computer science, that's known as an n-squared algorithm cost or computation cost. And it's actually very common in outlier detection because we have no labels. We are letting the data speak for itself. We have to figure out the relationship between all the data points. We have to figure out what's normal and what's not normal across many different dimensions. And this means comparing every point to every other point. So it's expensive. How expensive? So this is the chart of kind of n squared. So if you put 10 rows in, you've got to do 100 comparisons. If you double the size of the data set, you put 20 rows in, you suddenly have to do 400 comparisons. It's actually slightly less than that, this is what an n-squared algorithm cost looks like. Now, we have cloud computing. We have really big computers in the cloud, servers that have gigabytes of RAM and lots of processing power. Surely this isn't going to be a problem. Well, turns out it actually is, and it's actually quite a big problem, and it's quite hard to solve, right? I took a real world example, and this, again, every piece of data I'm now going to show you is real, right? And it's been measured in the last week, right? So this means that we actually took the existing scikit SOS algorithm. This is the published version of SOS from the original author. This is his GitHub repo there. There's a link at the bottom. You can go and install the code and use it. You actually don't have to install the code from the GitHub repo. You can just install it by doing pip install scikit sauce, right? And this means that it can be installed as a package and anybody can use it, right? So you can go and do this yourself. So what I did was I built a data set with, there's basically 4 columns in this data set, vaguely similar to how MindBridge, the amount of columns that MindBridge uses. I put in 5,000 rows and 10,000 rows and 20,000 rows. And then I fitted a line to it, right? So this is the actual data is the blue line, and the kind of orange line is the line that's been fitted to this data set. And you see the equation up above is the equation for the line. This tells you how to model X versus Y if you needed to predict a value. And that R squared equals 1, that's a measure of how well the prediction fits the model, right? 1 is a perfect fit. So this means, and the big problem with this is this Y equals then some little number X squared. It's the squared part that we need to worry about. This is confirming that stochastic outlier selection from the open source GitHub repos for this algorithm follows an X squared algorithm cost. So it's the perfect it's the perfect confirmation that SOS is an N squared algorithm. So we know that. Now, what happens if I start to increase the numbers, right? There's a reason, by the way, I stopped at 20,000 rows. The reason for that is that my laptop can't cope with more than 20,000 rows. I've measured it up to 100,000, but I had to use a really big computer to do it. So this is what the actual, if you take that line, and we know that this is the cost of SOS if you just take it off the shelf from open source, this is how long it will take to complete. Because cost, it's an N squared cost, but you can actually measure cost as time. So what I have here is the number of rows in a data set versus the amount of time the algorithm will take. So on 10,000 rows, it's working well. It only takes 3.5 minutes, a little under 3.5 minutes. It's great. But I times 10 that data set, I'm in hours, and then I get to 1 million, and I'm in 23 days. By the way, I couldn't run 1 million data points through this algorithm, even on a really big server. I tried this on a 24-core, 48-thread machine with 200 gig of RAM. I can get to 100,000. I can't quite get to 200,000 on that machine, and that's because, you know, based on the calculation that I was able to do 1 million, I'd need 8 terabytes of RAM, and that's exotic hardware. 8 terabytes is, you can do that today, but to process 1 million rows in a SOS, that's a very expensive process. So, and as it goes up, as you get to the tens of millions, 50 million, 100 million, 500 million, you see it starts to take years. And by the time we're at 500 million, we're at 15 millennia. That's how long we have to wait for that data, for that SOS algorithm to complete. So this is a big problem. I'm going to say that this basically makes the algorithm useless, right? It's really clever. It works really well on the data sets that we give it. But if I can't do it at industrial scale, if I can't do it at the scale of the ledger of a business, then it's no use to anyone. MindBridge chose to use SOS 6-7 years ago, and we've been on a journey to make it scale and scale and scale. And I'm going to talk to you a little bit about how we did that. So this is the state of the world if you just go and get the algorithm today off the shelf. This is the latest version as well from just a few days ago. So we need to flatten the N squared curve. I mean, in COVID, we talked about flattening the curve. We need to flatten the N squared curve for this algorithm. So how do we do this? So there are normal scaling strategies for SaaS. You may have heard me talk about our platform, how we scale our platform in the past. So there's a couple of strategies that are typical to use. So scaling out horizontally. This means taking a copy of the thing that you do and having 2, 3, 4 of them, right? This is really good for scaling to numbers of users, or if you have a problem that's easy to separate and compartmentalize. Scaling for users, it works really well. You have to be able to separate those processes. Now, the problem with calculating affinity, it's every point to every other point, right? This means that every point has to interact with every other point. So it's quite hard for that to scale out meaningfully. Another scaling, and this is very typical in scaling in terms of data volume, is to use things like sharding. It's often used in database schemes where you essentially store one part of your data on one disk and then another part of your data on another. It's also how things like RAID hard drive works. MindBridge uses this as well in our data storage. We use sharding methods. It's also a bit of a horizontal scaling capability, but it's great for data scaling when the data needs to live in one place or another and you want to query it, right? This is a great way of doing it. How MindBridge has thought about scaling our pipeline in the past has been, we actually use a couple of different methods, and I'm going to talk in more detail about these in a second. We have a certain size of computer that can handle what we call a normal load. And then we have workloads that we call heavy workloads. And basically how we manage heavy workloads is that we provision the largest machine that Microsoft Azure will allow us to, and we use that for these kind of heavy workloads. And the reason for that is the more stuff that we can hold in memory at one time, the faster the algorithm will go. The moment you go to a cluster scenario, you spend a lot of time communicating between nodes in the cluster, and it becomes super expensive, right? So if you can do something in normal, the world is good, it's going to happen quickly. Heavy is when things get a little bit bigger. Clustering is another option, but it's likely to be very slow, right? So if we can do it in heavy, it'll work. Scale by Kiwi, this is a phrase from IBM. Kiwi, it's not about, Kiwi as in the country, New Zealand. It stands for kill it with iron. Iron is the term for a big server in IBM speak. So heavy is a Kiwi strategy. It basically means go big, right? And see if you can cope if you go big. We've used these two strategies most of all in MindBridge. We've avoided cluster scenarios because the communication cost means you'll be waiting a very long time for algorithms to complete. Now, which one did we use for SOS? Well, basically we used all of these, but none of them are sufficient, right? You cannot achieve the scale that you need using these conventional SAS scaling approaches. You have to do something else, right? And this something else is often quite complicated. So a little bit about our architecture, and again, this is an old architecture diagram from I think this dates back to 2019. One of the things that we did back then was we designed our infrastructure to scale. Most of the design decisions we made in 2019, so this is 3 years ago now, were all about servicing more types of data and higher scale. So we created something that we call pipeline as a service. So we have multiple different pipeline types. They actually use different underlying technologies because we recognize that different types of pipelines are better at different things. And we have a lot of algorithms to run with a lot of different variety in them. So pipeline as a service basically is something that allows us to select which kind of pipeline is going to be required and configure it appropriately for the given data set. We actually have something in this diagram. It's kind of almost in the middle, called the collider, LSC. That's called a large spreadsheet collider. That's essentially the process that assigns the job to the particular pipeline and configures it to work, right? The other thing is we're able to use different types of machine learning library because we can configure the pipelines differently. They're different technology bases. This means we say, this algorithm works really well in this circumstance, we'll use it over here, but in this circumstance, we're going to use a different technology base. We also have something called the multi-temperature storage. This means that there's certain data that we require to be very fast, and it's stored in active hot memory. And there's certain types of data that we can cope with it being slower to access. So for example, let's say you're in an audit. At the time you're analyzing the data from a given company's finances, you want really rapid response times. But you're not going to, after the audit is finished, you're not going to look at that data for another few months, might be 3 months, might be 12 months. So the idea here is that we have rapid, fast access storage when it's needed, but we can also store things in cold storage. So we can basically take something out of hot and store it in something cooler or cold, and then we can bring it back as it's needed. So if someone logs in again and says, hey, okay, we're back. We want to look at this again. It will rehydrate from cold storage and come back to life. The other piece that we focused a lot on was configurability in the platform, and we have lots of different configurable platform components today, and you'll have seen multiple releases this year and the previous year, all adding extensive configurability to our platform. But I want to talk specifically about how we scale SOS. So we've been talking about calculating affinity versus calculating as being the main part of this algorithm. Calculating affinity is just one step in this algorithm. There are, as you can see here, there are 4 main steps to this algorithm. One part is calculating dissimilarity. That's actually measuring the distance between all points. So there's simple things you can do there, like you can save memory when you calculate dissimilarity, because it's just simply the distance between points. You can use half the memory from if you have a matrix of all points to all points. the two values are going to be the same. One of them is point A's distance to point B, and the other one is point B's distance to point A. It's a symmetric relationship, so it's exactly the same. So you can actually have the memory you use when you're calculating dissimilarity. You don't need to use all of it because it's a symmetric relationship. That's one of the things where you have to really understand the algorithm to be able to optimize it. Now, the problem with that's great, we've saved on dissimilarity, but to calculate affinity, it's not symmetric. It's an asymmetric relationship. My affinity, A's affinity to point B doesn't have to be the same as B's affinity to point A. It's asymmetric. This means you need all of that memory back, right? So saving half the memory at a previous step doesn't really help you because you're still going to hit this massive n squared problem once you calculate it. So how do we solve this? Well, we use things like libraries, as we showed, using the best possible pipeline to suit the problem, using libraries that are accelerated, typically at the hardware level. These are kind of fairly obvious statements if you're a data scientist or a software engineer. We can also do things like make the data smaller, compress it, summarize it in some way. We can also think about using memory more efficiently, or maybe not using memory at all. That's actually often a possibility. If we can stream the data through an algorithm, we don't have to use very much RAM at all. Sympathetic reading and storing or transmitting of results. So when you have a cluster, you're always transmitting data between nodes. If you can do that the lowest number of times possible, when you're reading, to read in a particular way that is sympathetic to the hardware underneath. So read a block at a time, read from the start of the file to the end of the file. Don't go back and forward through the file because many people are using the server you're on. All these things are ways of improving the performance. Another way is organizing the data that you're going to process better. Maybe you sort it, probably a bad idea, but you could sort the data from, like we were talking about in Excel, from high to low, and maybe that will help you. It probably won't help you in a multidimensional problem. And that's where you need to rely on clever things like this thing that's called a Hilbert space filling curve, right? So so when you have a two-dimensional space, this is a two-dimensional space filling curve. There is one point that enters the space and one point that leaves. And then this little line wiggles through every point. When you start to look at this in 2 dimensions and 3 dimensions, you'll see that you can still draw these space filling curves to almost any shape, right? And there's one entry point, one exit point, and this little line will wiggle through every point in space through it. Now, what's interesting about these space filling curves, particularly the Hilbert space filling curve, is that it has this handy capability of being dimensionally aware. So if I have a point, each point in this wiggling line has a number, it's called its Hilbert number, and things that have a similar Hilbert number are close to each other in space, whether it's 2-dimensional or 3-dimensional. And that can be really handy, because if you're trying to find your nearest neighbor, you need to find something that's got a Hilbert number that's close to yours. And you can start to look out larger and larger Hilbert numbers. And so this is a property that allows you to retain the dimensionality of something as you're processing it. So super useful. I'm not saying that's how we did it with SOS, but these are the types of methods that you need to use. It's highly involved and it's very complex. So I want to talk to you, okay, we've done this. We have actually gone through a process over many years, optimizing algorithms like SOS. And remember, SOS is just one algorithm out of many. There are 32 control points in our default GL analysis today. This is just one of them. This is the results of our team spending time optimizing. So this is the example on the left that we showed you earlier. This is the X squared, the real X squared data that we got out of using the off-the-shelf open source. And this is what our platform looks like today. So I took this isn't all the data points from our pipeline runs. This is a sample of them. You can see, do you remember we talked about what, 1 million rows in the original scikit-learn taking 21 days and requiring 8 terabytes of RAM. There's no server, by the way, in our infrastructure that's even close to a terabyte of RAM. See, the scale here starts at 20 million and it goes to about 120 million. What you can see is I drew a line through this, and this is the line. Notice that y equals some small number x. There's no squared in it. We have actually been able to take n squared algorithms and turn them into n, right? So the cost is a flat line. This means that we have the ability to perfectly scale high cost algorithms like stochastic outlier selection. So again, a hard problem to solve, took us years, right? But you can see we've been successful at flattening the curve and scaling the algorithms so that we can cope with almost almost any volume that is reasonable. So the other thing is, disclaimer, your mileage may vary. There are factors in our algorithms which are things like how many accounts there are in a given entity, which impact the performance of the algorithm set. And that's why it's not a perfect line. You can see there's some points are higher, some points are lower. That's fairly normal for our pipeline because there's lots of algorithms in there and we're always making it better. We're always looking at ways of tuning and going faster. So again, a huge effort by the team. This is how we took something that would take years and we've turned it into something that now takes hours. So at 10,000, 3.5 minutes, we're typically doing it in 2 minutes. That doesn't sound impressive, but there's a certain cost to firing up a large spreadsheet collider. It doesn't happen instantly, and your pipeline needs to be reserved for you, as an example. So these are real run times out of our production system. At 10,000, something would take 5 hours. I can run 10,000 on a laptop and a large server. 10,000 takes 80 gig of RAM on scikit-learn. It doesn't require very much memory at all in our production cloud. That happens in 4 minutes. And by the time you get to 50 million, you're at 158 years. You're going to be waiting a long time for the open source algorithm. You're going to be waiting about 11 hours using MindBridge. And that's because of the number of comparisons that 250 quintillion comparisons that Leighton was talking about earlier. We're getting close to that. So the achievement that we had this year, which is really unprecedented and unique to MindBridge, is that we were able to process over 500 million rows in a single analysis, right? It did take many hours, but we were able to do it. And that's at that scale, it's at the scale of the largest entities in the world's financial data. And we can partition that as well, and we can do more, and we're continuing to do more. And just for context, we have processed 53 billion entries. This slide maybe is a little old. So we've processed 53 billion rows since 2018, right? And if you were to do that with the off-the-shelf algorithm, you would be waiting 171 million years. That's a really long time. That's actually the start of the Jurassic era. So if you started the analysis back then, it would complete right about now. So you'd be waiting a really long time, but it's a credit to the MindBridge team, our technology team, and our pipeline team, that we've been able to achieve these numbers and we've been able to make this available to our customers. So just a point on why algorithm validation matters. Clearly, to achieve this kind of performance, we have to do lots of things to the algorithm. We have to figure out how to scale it. We have to figure out, perhaps how to index and map data across. And we have to make sure that when the data comes out the other end of that algorithm, that it is still fulfilling the desired purpose. It is still performing stochastic outlier selection. And that's one of the reasons, not the only reason, but it's one of the reasons why not only do we validate our algorithms ourselves, but we have a third party do it, right? And they assess our algorithms for whether they're explainable, robust, whether they include bias. And again, this report is available to any paying customer. So you can be assured, not only do we say our algorithm works the way it does, but a third party has gone and analyzed the outcome of our algorithms, compared it to the desired outcome, and has confirmed that it does work. So why do we need scaling? Why did we care so much about scaling these algorithms? Well, we talked about unsupervised machine learning being something that can find unknown unknowns, and it was our purpose from the very beginning. So we have to find a way of making these methods scale for our purpose. But we've solved this problem. We solved this problem for existing customers, but we're also thinking to the future. So this was on the roadmap that I've shared with clients probably over the last 2 years now. We talk about prepackaged ledger analysis, or a GL analysis, the most popular analysis we have, getting to configurable analyses, moving on to linking and matching data sets together, and then being able to connect unstructured data. So we are, the little orange arrow kind of tells you where we are in our journey. A part of being able to do configurable analysis templates is we know there's going to be more types of data coming into our platform. This means that volume is increasing. It also means that the algorithm types we're using more types of algorithms today than we've ever used in the past. This means we need to build on a solid foundation and a platform that can scale to meet the demand of the largest businesses. So as we move through our configurable analysis journey, we really needed to solve the platform scale problem, and we think we've cracked it. We're not done yet, by the way. The team is not going to stop working on scaling. We think there's more that we can do. But a part of our journey ahead, as we look at things like linking and matching, that is going to increase the problems that we have to solve. Let me just explain that for a second. So you may be in a meeting or in a session in Edge in the next few days where you're going to hear about modeling business processes and particularly like purchase to pay as an example. In this kind of scenario, we're talking about multiple different ledgers, and we're talking about connecting multiple different data files together. So remember that n squared problem? Compare this thing to everything over there. That can happen now in multiple different ways. So flattening the curve is not just important for a single algorithm like SOS. It's important to the future of our business process modeling capability, and it's important to how we think about linking data sets together in future. So a couple of key takeaways. Data problems are hard, and there's huge competitive advantage if you can get it right. Using these technologies that can do things like unsupervised machine learning at scale is really unlocking huge amounts of value. And the good news is we've built our platform to scale, right? And it scales to the most demanding workloads that we see today, and we're preparing it for the future, which is even more. So I wanted to ask you, this is a little call to action. I'm at my time, so I'm going to get pulled off stage. If you are interested in collaborating with our technology team on new types of analysis, and if you would like to be an early adopter on something like payroll, vendor, inventory, or procure-to-pay processes, please get in touch, and we'll be super happy to involve you, and you can work with us to shape the future. So with that, I'm gonna stop my session now. I want to thank you all for attending. I'm going to recommend again that you stick around and hear about some of our future capabilities from Rachel. And please enjoy this week. We're here for our clients. We're here. We are all ears, and we want to hear anything, any feedback you have. It's just super valuable for us to be engaging at this kind of level with you guys. So anyway, thank you so much.